x be the number of meters a bus has gone at a time x in seconds. A lot of times you'll see in books this will be, instead of x, this will be t and this will be t, right? But we can use x, it doesn't matter what the variable is. Find the instantaneous velocity at a given time. So what is instantaneous velocity? Well, velocity, okay, is a speed with direction, okay? So when we look at average velocity, we're looking for the average change in distance. So let me just write this down for you because this is important, especially if you're going to be taking physics. So your average velocity equals the average change in position. So the average change in position over the change in time. Meaning, like, if we drive 6 miles in 1 hour, our average velocity excuse me, is 6 miles per hour, right? If we drive that same 6 miles in 2 hours, our average velocity, or you can think about it as average speed, is 3 miles per hour. Okay. Now, instantaneous velocity is the velocity at one exact point in time. It's like if you were driving and you look down at your speedometer, right? And it said you were going 42 miles per hour. At that exact moment, your speed is 42 miles per hour. That's an instantaneous velocity. It's at that exact moment. It doesn't take it over an average amount of time, right? Because over an average amount of time, you could stop at a stop sign, you could go through a school zone, whatever it happens to be, so your velocity is going to change. We want to know it at an exact moment. So what we need to do is to find an instantaneous rate of change, which velocity is. Velocity is it's a change of position over a change in time. The instantaneous has to deal with the tangent line and specifically the slope. I just did double parentheses here. Okay, but that's fine. So here's what we're looking at. We've got some function right here which describes the meters a bus has gone. Okay, and so for example, at x equals 0, the bus has traveled 0 meters. And at x equals 1, the bus has traveled 4 meters. So its average velocity, I'll get to the question in a second here, but its average velocity is going to be equal to its change in its position, which is 4 meters, over its change in time, which is 1 second, right? We went from 0 seconds to 1 second, and our change in our position was 0 to 4 meters. So we would say that the bus had an average speed or an average velocity of 4 meters per second. Okay? Now, it's clear that the bus was speeding up, right? It went from a standstill. It wasn't moving at all. Okay? To all of a sudden it's moving, right? Now we can argue whether we can go into negative time values or not. Okay, so let's not do that here. But we can say that, okay, the bus is increasing, right? And in fact, if we go to x to time equals 2, we'd have 2 squared plus 3 times 2 is 4, plus 6 is 10. So in the first second, we increased by 4 meters. In the second, between second number 1 and second number 2, we increased by 6 meters. So we're obviously speeding up, okay? But now here's the question. Not what's the average velocity at 4, but what's the exact velocity at 4, the instantaneous velocity? Well, first we need to figure out how far away is the bus at 4 seconds. Well, the bus is 4 squared plus 3 times 4, so that's 16 plus 12, and that's going to be equal to 28, it looks like. So the bus is 28 meters away from where it initially started at time 0. Now, what we would do, and here's the big picture, what we would do is we'd say, okay, let's take a look at that graph. Well, that graph looks something like this. And so at 4 seconds, we know the distance is going to be 28 meters, right? Okay, good. Now, what we want is we want the rate of change. We want the change in the y value divided by the change in the x value, but we want it at this exact moment right here. So what we're really looking for, the thing that tells us rates of change, is the slope of the tangent line, or the slope of the secant line, right? What I was calculating up here, okay, when I was doing the differences between here and calculating averages, I was calculating slopes of secant lines. Down here, I'm calculating the slope of the tangent line because tangent is instantaneous, secant is average. Okay, so I need the slope of this line. Well, what I'm going to do is I'm going to grab another point that's just off of 4 seconds. So we're going to go a little bit over. We'll call that a little bit change in x. That's a single variable by itself, just delta x. So over here, I don't know what delta x is. Maybe delta x is 1 second. Okay. In fact, you know what? Let's do that. Let's say delta x is 1 second. So now we're over here at 4 plus delta x, which is 4 seconds plus 1 second, or 5 seconds. And then what I do is I go up to the function, okay? And then I go over and I say, okay, well, what is the height at 5 seconds, right? At 5 seconds. Well, the height at 5 seconds of the function is 5 squared plus 3 times 5, which is 25 plus 15, or 40. So we're at 40 meters. Okay? So, if we take a look at this line and its slope, the slope of this line is going to be 40 minus 28 over 5 minus 4. And so that's going to give me 12 over 1, which is 12. Okay, so that's 12 meters per 1 second. So the average velocity is 12 meters per second between 4 and 5 seconds. So the bus is traveling at 12 meters per second. If you look here, guys, what I calculated was the change in the y over the change in the x, which was the slope. So the slope of the green line tells me the average velocity. That's the big connection here. Now, here's the cool part, and here's what calculus is all about. What I'm going to do is I'm going to take that change of x and I'm going to make it smaller. Okay? Instead of making it 1, we can make it 0.1. Okay? And what that would do is that would move this green line closer, right? And I'm going to do it in red here. So let's say I made the change of x smaller. So instead of the change of x being 1, I made the change of x being 0.1. Then I would go up to the line. I would come over. I would find this value right here, which I'm just going to put a question mark for right now. And then I would take that point and this initial point here, and I would draw the line in between, and I'd figure out this guy's slope. Now clearly this guy's going to be less than 12, right? Because the green line was 12 and the red line's less steep. But which one is the better approximation for the blue line? Well, of course the red line is, because we moved change of x to be smaller. So here's what we're going to do. We're going to, instead of letting change of x be an actual number, we're just going to call it change of x. Okay? So if we just let it be change of x, well, I don't know what change of x is. It's just a number. Okay? I'm going to do this one here in yellow. So now what I'm going to do is I'm going to say, well, we don't know. Let me erase a bunch of this because it's just stuff all over the place in here. I wanted that blue line, but we'll put it back. Sorry, I'm erasing a little bit more than what I wanted, but we need it clear so that we can see what's going on here. So what I want is I want the slope of this blue line, right? The tangent line. So what we're going to do is we're going to take an arbitrary, and I'm gonna move it over just a little bit so that we have room to see it. But just remember, this can be as small as we want. I'm gonna take an arbitrary change of x. So of course this guy's at 4 plus whatever change of x is. And then I'm gonna go up to the function. Okay, we're just gonna go like this so that we can get it on here. And then I'm gonna take it over. Oops. Good enough. Okay, and we're going to take it over. And we're going to figure out the slope of this line. And then what we're going to do is we're going to let change of x get really, really close to 0. Okay, so if this is 4 plus delta x, what is its height? Well, the function f was equal to something squared plus 3 times something. Okay, so then f at 4 plus a little bit must be 4 plus a little bit squared plus 3 times 4 plus a little bit. That's this guy right here. That's the height. Okay, so what we're going to do is we're going to take that height and we're going to subtract off this height. And that's our change in our y value. Okay, so it's going to be 4 plus delta x squared plus 3 times 4 plus delta x. But then we have to subtract off f at 4, which we know is 28, and we're going to put that in there in a minute. And then we're going to divide that by the change in the x. Change in the x, by the way, is 4 plus delta x minus 4, which, look at that, when you do it, it's just delta x. So this is the change in the x. This length right here is the change in the y. So now it's just algebra here. This, if I do the top out here, it becomes 16 plus 8 delta x plus delta x squared plus 12 plus 3 delta x minus 28, right? Because that's f of 4. And that's over delta x. So what cancels here? Well, the 16 plus the 12 is 28. And so that cancels with this 28 right here. And if we factor out a delta x, we get this. 8 plus delta x plus 3 over delta x. If we cancel those guys out, whoops, we get just 8 plus delta x plus 3. So as delta x goes to 0, as it gets super small, this piece right here gets super small as well. So 8 plus delta x plus 3 goes to 8 plus 3, which is 11. So the slope of the blue line, because what we did was we took this point right here, this is the cool part, we took this point right here and we moved it closer and closer to this point right here, so they're right next to each other. Okay, just they're so close to each other that you can think about not being able to fit another point in between them. Okay, so that's how close they are to one another. And we got 11 out, so the slope of the blue line is 11. Well, what is that? Well, 11, the slope is the change in the y over the change in the x. So the change in the y is 11. It's 11 over 1. So the y value is in meters. The x value is in seconds. So the bus, its instantaneous velocity is 11 meters per second. Okay, and that's it.